In this lecture, we are going to look at methods of circuit analysis as applied to AC networks. In the analysis of AC networks, methods of circuit analysis are applied using the same principles as used for DC networks. The difference is that complex impedance is used in place of resistance, and voltages and currents are represented in phasor form. The methods that we are going to look at are mesh analysis, nodal analysis, and star-delta conversions. Sources can be classified as independent or dependent sources. An independent source is a source whose magnitude is independent of the network to which it is connected. In other words, it displays the same terminal characteristics in different networks, and even if it is completely isolated. A dependent source or controlled source is one whose magnitude depends on the network to which it is connected. In other words, the magnitude depends on the voltage across or current through another element in the network. In the illustration, on the left, the magnitude of the voltage source depends on the voltage across a resistance. On the right, the magnitude of the current source depends on the current through a resistance. We can also have situations where the magnitude of voltage source depends on current and the magnitude of a current source depends on a voltage. We can convert an AC voltage source into an equivalent AC current source. To convert an AC voltage source into a current source, the current is calculated as the AC voltage rating over the source impedance. To convert an AC current source into a voltage source, the voltage rating is calculated as the current source rating times the source impedance. The impedance remains the same when we convert from one form to the other. It only changes the position. In a voltage source, it is connected series to the source, and in a current source, it is connected parallel to the source. In this example, we want to convert each given source into an equivalent source in the alternate form. For circuit A, we are converting from a voltage source into a current source. The source impedance is 3 plus J4. The equivalent current source rating is equal to voltage rating over the impedance, which works out as 20 amps at an angle of minus 53.1 degrees. In circuit B, we are converting from a current source into a voltage source. The source impedance is J6 parallel minus J4, which is equal to minus J12. The equivalent voltage source rating is equal to the current source rating times the impedance, which works out as 120 volts at an angle of minus 150 degrees. Let's look at the mesh analysis method. The steps followed when using the general approach are: 1. Change all current sources to voltage sources. 2. Assign a distinct current to each independent closed loop of the network. 3. Indicate the polarities within each loop for each impedance as determined by the assumed direction of the loop current for the loop. Number 4. Apply KVL around each closed loop. Number 5. Solve the resulting simultaneous equations for loop currents. The loop currents can then be used to calculate any other quantities in the circuit. The steps followed when using the format approach are: 1. Convert all current sources to voltage sources. 2. Assign a distinct loop current to each independent closed loop in a clockwise direction. 3. Form the mesh equations. The first term on the left-hand side of each equation is the product of the loop current and the sum of impedances through which the loop current passes. Subsequent terms are mutual terms. Each mutual term is a product of the mutual loop current and the mutual impedance. Mutual terms are subtracted from the first term. The right-hand side is the algebraic sum of the ratings of voltage sources in the loop. Number 4, solve the resulting simultaneous equations for loop currents. Let's illustrate the mesh analysis format approach using an example. Let's begin by calculating the impedances for the respective branches that make up the network. The impedance for the branch that contains R1 and XL1, denoted as Z1, is 2.23 ohms at 63.43 degrees. The impedance for the branch that contains XC and R2, denoted as Z2, is 8.94 ohms at minus 63.43 degrees. The impedance for the branch that contains XL2, denoted as Z3, is 6 ohms at 90 degrees. To make the circuit look simpler, let's redraw it with branches represented using their respective impedances. We can identify two independent loops. Let's assign the respective loop currents as I1 and I2. For loop 1, the impedances through which the loop current flows are Z1 and Z2. Therefore, the first term is I1 by Z1 plus Z2. The only mutual current is I2 and the corresponding impedance is Z2. Therefore, the only mutual term is minus I2 Z2. The voltage sources in the loop are E1 and E2. Therefore, the right-hand side is equal to E1 plus E2. After substituting for values for Z1, Z2, E1, and E2, the equation works out as shown. For loop 2, the impedances through which the loop current flows are Z2 and Z3. Therefore, the first term is I2 by Z2 plus Z3. The only mutual current is I1 and the corresponding mutual impedance is Z2. Therefore, the only mutual term is minus I1 Z2. The voltage source in the loop is E2. Therefore, the right-hand side is equal to E2. After substituting for Z2, Z3, and E2, the equation works out as shown. You can solve these equations simultaneously as an exercise. For checking purposes, I2 has been worked out for you and is equal to 1.27 amps at minus 86.92 degrees. Another example, we want to use the mesh analysis format approach to write the mesh equations. We are not given values of components in the network. Therefore, we represent the impedances of the respective branches in the network as Z1, Z2, Z3, and Z4. The simpler network appears as shown. We can identify three loops. We assign them the respective loop currents I1, I2, and I3. For loop 1, the impedances through which the loop current flows are Z2 and Z4. Therefore, the first term is I1 by Z2 plus Z4. The mutual loops are loop 2 and loop 3, and the corresponding mutual impedances are Z2 and Z4. Therefore, the mutual terms are minus I2 Z2 and minus I3 Z4. The voltage source in the loop is E1, therefore the right hand side is equal to E1. For loop 2, the impedances through which the loop current flows are Z1, Z2 and Z3. Therefore, the first term is I2 by Z1 plus Z2 plus Z3. The mutual loops are loop 1 and loop 3. The corresponding mutual impedances are Z2 and Z4. Therefore, the mutual terms are minus I1 Z2 and minus I3 Z3. There is no voltage source in the loop. Therefore, the right hand side is equal to 0. Loop 3, the impedances through which the loop current flows are Z3 and Z4. Therefore, the first term is I3 by Z3 plus Z4. The mutual loops are loop 1 and loop 2. The corresponding mutual impedances are Z4 and Z3. Therefore, the mutual terms are minus I1 Z4 and minus I2 Z3. The voltage source in the loop is E2. Therefore, the right hand side is equal to E2. Suppose we are given values for Z1, Z2, Z3, Z4 and the voltage sources as shown. Determine the loop currents as an exercise. Let's go into the nodal analysis. The steps for applying the nodal analysis method using the general approach are: 1. Convert all voltage sources to current sources. 2. Pick a reference node and assign a distinct nodal voltage to each remaining node. 3. Express each branch current in terms of the nodal voltages and the impedances between the nodes. 4. Apply Kirchhoff's current law at each node except the reference node. 5. Solve the resulting simultaneous equations for the nodal voltages. The nodal voltages can then be used to calculate other quantities in the network. The steps when using the format approach are: 1. Convert all voltage sources to current sources. 2. Choose a reference node and assign a distinct voltage to each of the remaining nodes. 3. Form the nodal equations. The first term on the left-hand side is the product of the nodal voltage at the node in question and the sum of the admittances tied to the node. Subsequent terms are mutual terms. Each mutual term is the product of the mutual nodal voltage and the mutual conductance. Mutual terms are subtracted from the first term. The right-hand side is equal to the algebraic sum of the current ratings of the current sources connected to the node. 4. Solve the resulting simultaneous equations for the nodal voltages. Let's illustrate the nodal analysis format approach using an example. We begin by calculating the impedances of the respective branches that make up the network. Z1 is the impedance for the branch that contains R1 and XL1. Z2 is the impedance for the branch that contains R2 and XL2. Z3 is the impedance for the branch that contains XC. Z4 is the impedance for the branch that contains R3. After that, we convert the voltage source into an equivalent current source. The rating of the equivalent current source is worked out as 1.94 amps at minus 48.81 degrees. Thus, the resulting circuit, after replacing the voltage source with an equivalent current source and the branches using the impedances Z1, Z2, Z3, and Z4, we can identify two nodes in the network. We assign them the respective nodal voltages V1 and V2. For node 1, the admittances attached to the node are 1 over Z1, 1 over Z2, and 1 over Z3. The first term, therefore, is V1 by 1 over Z1 plus 1 over Z2 plus 1 over Z3. The mutual node is node 2, and the mutual admittance is 1 over Z3. Therefore, the mutual term is minus V2 by 1 over Z3. The current source attached to the node is I2. Therefore, the right-hand side is equal to I2. For node 2, the admittances attached to the node are 1 over Z3 and 1 over Z4. Therefore, the first term is V2 by 1 over Z3 plus 1 over Z4. The mutual node is node 1, and the mutual admittance is 1 over Z3. Therefore, the mutual term is minus V1 by 1 over Z3. The current source attached to the node is I1. Therefore, the right-hand side is equal to I1. As exercise, substitute for Z1, Z2, Z3, and I1 and I2 using the actual values. Then solve the equations for the nodal voltages. Another example, we want to use the nodal analysis format approach to write the nodal equations. We are not given the values of the elements in the network. Therefore, we just represent the respective impedances of the branches in the network using the names Z1 through to Z6. Thus, the circuit after we redraw it with the branches represented using the respective impedances. We identify 3 nodes in the network. We assign them the respective nodal voltages V1, V2, and V3. For node 1, the admittances attached to the node are 1 over Z1 and 1 over Z2. Therefore, the first term is V1 by 1 over Z1 plus 1 over Z2. The mutual node is node 2, and the mutual admittance is 1 over Z2. Therefore, the mutual term is minus V2 by 1 over Z2. The current source attached to the node is I1. Therefore, the right-hand side is equal to I1. For node 2, the admittances attached to the node are 1 over Z2, 1 over Z3, and 1 over Z4. Therefore, the first term is V2 by 1 over Z2 plus 1 over Z3 plus 1 over Z4. The mutual nodes are node 1 and node 3. The mutual admittances are 1 over Z2 and 1 over Z4. Therefore, the mutual terms are minus V1 by 1 over Z2 and minus V3 by 1 over Z4. The current source attached to the node is I2, and it is leaving the node. Therefore, the right-hand side is equal to minus I2. For node 3, the admittances attached to the node are 1 over Z4, 1 over Z5, and 1 over Z6. Therefore, the first term is V3 by 1 over Z4 plus 1 over Z5 plus 1 over Z6. The mutual node is node 2, and the mutual admittance is 1 over Z4. Therefore, the mutual term is minus V2 by 1 over Z4. The current source attached to the node is I2. Therefore, the right-hand side is equal to I2. Star delta transformations may be necessary during the calculation of overall impedances for networks. To convert a delta network into an equivalent star network, the value of each star impedance is calculated as being equal to the product of 2 closest delta impedances divided by the sum of all the delta impedances. Using the illustrations shown, These are the formula that may be used to calculate equivalent star impedances Z1, Z2, and Z3 when given delta impedances ZA, ZB, and ZC. To convert a star network into an equivalent delta network, the value of each delta impedance is calculated as being equal to the total of possible product combinations of star impedances divided by the furthest star impedance. Using the illustrations shown, these are the formula that may be used to calculate equivalent delta impedances ZA, ZB, and ZC when given the star impedances Z1, Z2, and Z3. We have an example here. We want to find the total impedance of the network. We realize that we cannot reduce the circuit any further using the series parallel reduction approach. Therefore, we need to perform a star-delta transformation. Let's change the top delta connection into an equivalent star connection. That is the equivalent circuit after the transformation. Z1, Z2, and Z3 are the corresponding star impedances. The star impedances are found using the rule that the star impedance is equal to the product of two closest delta impedances divided by the sum of all the delta impedances. The impedances are worked out as Z1 equals 3.84 plus J 1.11, Z2 equals 3.84 plus J 1.11, Z3 equals minus 1.92 plus J 2.56. Z1 and Z4 are in series. The series combination denoted as ZT2 is equal to 3.84 plus J 4.11. Z2 and Z5 are in series. The series combination denoted as ZT1 is equal to 3.84 plus J 3.11. ZT2 and ZT1 are in parallel, and the parallel combination is in series with Z3. Therefore, the total impedance is equal to Z3 plus Z1 plus Z4 parallel Z2 plus Z5. The answer works out as 1.23 ohms minus J 2.0 ohms. Another example, we want to find the total impedance. Again, we need to perform a star-delta transformation. Let's convert the inner star network into an equivalent delta network. Thus, the circuit after we perform the transformation. ZA, ZB, and ZC are the corresponding delta impedances. The star impedances are equal. Now, if the star impedances are equal, each delta impedance is equal to 3 times a star impedance. Therefore, the impedances ZA, ZB, and ZC are all equal to 3 plus J6. The circuit has now been reduced into a series parallel network. We can then use the series parallel reduction methods to calculate the total impedance. We obtain it as 2.24 ohms at an angle of minus 63.43 degrees. I recommend that you do these questions from chapter 10 before you proceed to the next lecture.